Okay, we already discussed the VLSI implementation of neural networks, and another field that you can successfully implement neural networks is the field of medicine. Okay, typically there are algorithms in, of course, medical area. Let's say you have a number of questions that you are asking to a potential case, okay, and you're asking frequent coughing, chest pain, shortness of breath, wheezing, repeated bouts of pneumonia or bronchitis, hoarseness, coughing up the excess of mucus, bloody or rust-colored phlegm. Okay, so depending on the answers, you are trying to give a diagnosis. Okay, I mean, it is possible to extend the number of questions. It is possible to supplement the um, this questionnaire together with some, blood analysis. Okay, I mean, it is possible to collect some data, some lab inspections or whatever, and those are your inputs to a neural network structure, and you decide on whether there are or some problems, some health problems for a patient. Okay, so train the neural network for the data of prior instances and update as new instances occur. I mean, if you have, say, for example, 1 million previously recorded cases, then it becomes kind of easy for you to determine or diagnose certain diseases without the intervention of a human doctor. Okay, so neural networks could be a good alternative for medical applications. There are journals, I mean, like expert systems or medical informatics or whatever. So you can go to Web of Science or Science Direct. You can see those journals and read the relevant papers that use neural networks for medical applications. And in finance, it is of course possible to predict bankruptcy, for example. There are books on it, bankruptcy prediction. If you see the indicators 1 month before bankruptcy or 2 months before bankruptcy, you could take precautions to prevent it. So it is indeed a kind of anomaly detection, which is now a very famous problem for most machine learning algorithms. And neural networks is another algorithm that falls within the field of machine learning. So it is possible to observe the numerical data and give some predictions about the trend or coming actions. So in stock market, it is possible to implement some applications. I mean, data for companies, some economic observations, some political observations, capital, changing capital, the speculations. You can grade the speculations, inflations, and all economic inputs to a neural network, and that neural network could provide you a number of investment actions. Okay, a number of investment actions. Is it possible? Indeed, it is very difficult, but there are chaotic, undeterministic inputs, like for example a political grade, okay, like for example speculation. So your neural network should be intelligent enough to process that input so that your suggested investment actions are meaningful. So the goal is to increase the amount of capital you have. Now the problem is to develop a intelligent or smart software that gives you some hints. Okay, That gives you some hints. We are kind of approaching to the end of my lecture notes. There is an open question in neural network stuff. Well, kind of regularization solves this problem to some extent. You are tuning the parameters of a, say, for example, this is a control architecture, an online control architecture, an emulator architecture. The problem here is that you are tuning the parameters online, but you should be able to give a guarantee for boundedness of your adjustable parameters, okay? No one of your adjustable parameters should go to infinity, okay, should grow unbounded. So it is something bad. This is system dynamics. This is the emulator weights. It's a dynamical structure, and this is the controller weights. It's another dynamical structure. So you should say that this, omega ijl's emulator weights and the controller weights must converge to a constant. If this happens, or if you can develop that if you can show that there is a ball, all dynamical activity takes place within that ball, there is a certain upper bound for this constant, then your system could be considered as a reliable, secure system, okay, a safe system. If not, then you should know that your parameter norm is tending to infinity, and this is a stability problem. Years ago, there were papers showing the results for only the first line. I mean, the system works fine, but the authors say nothing about the parameters of the neural network, whether they go to infinity or minus infinity is unknown. Okay, those are, I mean, poor papers of the past. Okay. Okay. In this part of the course, I will explain you a kind of reinforcement learning. Reinforcement learning is an important topic. It has been an important topic for the last 5 years, and probably it is going to be an important topic for the coming 10 years, because machine learning and the applications of it require solutions of or algorithms of reinforcement learning. There are very, very good books about it. Please find them, buy them, or download them and read them. In this part of the course, I will explain you the jackpot journey, okay? So we're going to find the gold by developing a search policy, and we will apply a reward and a penalty algorithm. There are signposts, and you are now at point signpost A. Okay, signpost is a box. Okay, so each signpost has black and white stones. There are, baskets, and within those baskets you see black and white stones. If you are at point A, if you pick a stone which is black, then you go down. Down means you go to signpost B. If you pick a stone which is white, you go up. The next station is point signpost C. Okay? So you do this for each one of those steps until you go to the end. I mean, one of those red letters, J, I, H, or G, G. Okay? And the gold is at signpost H. Okay? The moral of the story here is that failure is the surest path to success. Okay, failure is the surest path to success. At a particular signpost, The probability of going down is the number of black stones in that signpost over the total number of stones, okay? And probability of going up is equal to the number of white stones within that particular box over the total number of boxes in that particular signpost. This should be clear. Say, for example, you started at point A, signpost A, you picked a stone which was black. Now you are at B, go down. You are at state B, you picked a stone, okay, which is white. So the next state is E because it is saying that it's going to take you go up, okay. And another stone, the last one is white. You go state I, okay. This is failure. So you have to apply the penalty scheme. Take away the stones that make you fail. Now, you will remove the white stone here, you will remove the white stone here, okay, and the black stone here, okay? White, white, black, okay. White, white, black. So the number of white stones will be one less in E, one less in B, and the number of black stones is one less in A. So the next person who takes this journey has a little information, a little information that makes his life easy because the number of black is little here, less here. The number of white is less here. So this path is penalized. Okay, this path is, but the algorithm is not advising A, B, E, I route. Okay, so the probability of A, B, E, I route is decreased. Okay, in a new journey, you are at state A, you picked up stone which was black, okay, and now the next station is B, you picked a stone, yes, the next station is E, you picked a stone which is black now, then you are at station H. This is success because you found gold. Apply the reward scheme. In the reward mechanism, you put the stones back into the signposts and put additional one with the same color. Now you are strengthening the probability of success with the success mechanism, reward mechanism, and you are decreasing the probability of failure. Okay, now let's say you are doing many voyages to reinforce. Okay, as you fail, the probability of the action that makes you fail is reduced by the penalty mechanism. As you succeed, the probability of the action that makes you succeed is strengthened. Okay, see the evolution of the probabilities. After 1,000 voyages, you see that this is telling me the change of the P down probability. This is the P down probability, okay? P down probability. If you are at point D, after 10,000 voyages, P down probability is 0. So there is no black stones here, okay? There is no black stones. All stones are white now, okay? After the 1,000 voyages, we have all black stones in signpost D. What about E? All stones are black for the signpost E. As you see, this is with a probability of 1. So all stones are black. You go down and find the gold. Okay. What happens for C? For the C, you see that this blue one, it takes you to point E, because if it guides you to F, you will lose, all right? So the probability at this signpost is all black stones, and it takes you to E. Blackstone probability is 1, okay? For the signposts B and F, it is close to 50-50%. You see, it is close to 50-50%, okay? And you see that for the B and F, for B, well, E and D are managed. For F, there is no chance to find the gold. So the probability is about the 0.5. But interestingly, for the point A, signpost A, you see that it tries to increase the probability of going down, okay? It is nearly 0.9. So you see that this probability takes you to signpost B, and when you reach B, it is easier to guide to the point or signpost H, okay? So there is a GIF file. I hope it works. Do you see the change? After 10,000, it will start over. Well, oh, this is showing me the same simulation, and I, well, produced my code in such a way that the thickness of each line is proportional to the probability, okay? Now see F, J, and I, these three nodes are separated from the rest of the network. So your algorithm does not recommend reaching point F, okay? Reaching point F. This is now very thin, this is thin, so these three nodes are now cut out, okay? Now let's see what happens to other cases. For E and D, these are very thick connections. With those connections, I find the gold with 100% probability, okay? So let's see what is happening to point A, this green line. When you compare with this red one, you see that it is recommending to go to point B, okay? So it doesn't matter what happens in these two connections, pink and red ones, okay? Your algorithm basically your algorithm guides you toward the thick lines. A, B, E, H, A, B, D, H are thick lines, okay? And they are most recommended. So the same happens to point G. As my algorithm runs, you see this gets thinner and thinner. So this point, the node G is basically cut out from the network, okay? And from the top left corner, you see the probabilities, change of the probabilities, okay? P down probabilities are given by blue ones, P up probabilities are given by the red ones, okay? So at point A, the probability goes up to 0.5, 6, 73, 75, 77. 0.78. 0.78 probability is given to here. 0.22 probability is given to this connection. Basically, no one is telling you that this network should be trained in a supervised manner. Basically, you are applying a reward and penalty mechanism, and with that mechanism, these probabilities are getting tuned, okay? This is a very nice algorithm to explain what a reinforcement type of a learning is happening, okay? So, no external teachers. I mean, no supervisory information is available. Only the input vectors will be used for learning in unsupervised learning. In unsupervised learning system, the system is called an agent, okay? The agent extracts the regularities, associations in the data, and the data contains several persistent features available redundantly. Say, for example, you have 1 million samples from a process, and that produce a kind of Gaussian curve. The mean of that Gaussian curve is a feature for that data set, okay? Unsupervised learning is used for data clustering, feature extraction, and similarity detection. And this similar input patterns excite different internal parts of a network, and this leads to development of specialized internal structures in the neural network. As an example, we can consider the winner-take-all algorithm. You are applying a 3x1 input vector to your neural structure, okay? And there is a matrix. That matrix is 4x3, and you multiply that matrix by a 3x1 input, you obtain a 4x1 output, which is tau, which is composed of tau 1, tau 2, tau 3, and tau 4, okay? So for each one of those output neurons, the net summation is given by Si, where I runs from 1 to 4, is equal to J runs from 1 to 3, sum omega ij uj. Fine, this is clear to us. We calculate this inner product, which is the activation level for all output neurons, and choose the neuron having maximum activation value. Say, for example, one of them has the maximum SI value, okay? And that is the kth neuron. Only the weights of the winner are updated, okay? The others remain unchanged. Sk is omega k transpose times u. This is the vector inner product, vector multiplication, okay, inner product. The next value, omega k t plus 1, is equal to omega k times eta times u minus omega k over the length of omega k plus eta u minus omega k. Basically, this normalization is done in order to obtain a vector with magnitude unity, magnitude which is equal to 1, okay? So there was a video, but I guess it does not work. It's not important. There are 4 clouds of points you see. When t is equal to 1, the 4 vectors are located like you see here. And after the 14th iteration, they are located as you see in this top right drawing. And the bottom left drawing, you see that after the 27th iteration, well, these 2 points are approaching the centers of those clouds, okay, those clusters. And after the 40 iterations, you see that nobody is telling you about the centers of those positions, but the algorithm finds the centers of those clusters, okay? Well, there may be several problems. I mean, you can ask how many clusters are available initially. Do we know them, okay? If we start with 5 such points or 2 such points, what would happen? These are all questions that you can write your own MATLAB code or Python code and see, okay? A nice algorithm, a very nice algorithm is k nearest neighbor clustering, which is subject to the same questions, okay? How many clusters are initially? If I choose more than the number of clusters or less than the number of clusters, what happens? Okay, these are essential questions. In our case, 4 clusters are available, and we have chosen 4 input neurons to find those clusters. Yes, as I already said, data may have more than 4 clusters, then the final vectors would converge at most to 4 of them. Okay. For example, data has 6 clusters and you have 4 neurons, and you find out 3 clusters. Okay. This is a possible case, I mean. Okay. We have initialized the weights to randomly chosen input patterns. This is because of the following. Yes. After random initialization, some weights can be far away from the data, and those weights get never updated. The procedure overcomes this drawback. Does it work? No. Okay, it's not a problem. This is the, these were the snapshots from several intermediate steps. It is possible for you to develop your own case. Okay. Well, we came to the end of my slides. Okay. Probably this is the last slide I will show you for this file. There are many different types of neural networks. I mean, this neural network research is a very hot topic, and I have introduced you a very basic, input-output computation, parameter tuning, constructing the loops, several example applications. But in the field of large-scale neural networks like deep networks or convolutional networks, if you have good computational capabilities like a GPU or a cluster, you could go into interesting research problems. Okay, every day there are many papers are being published, so closely follow the literature so that you can identify good research problems for your own research with your own professors. Okay, and you can develop you can come up with good papers. These are some very simple neural network structures, but I have shown you most of those structures in my discussion.